Welcome back to the Solar Monitor project. This is the ongoing quest to try and read DC signals from a hybrid inverter into the Myenergi app. So previously we looked at CT clamps, that's the AC type, both with and without a burden resistor, and we then made a custom CT clamp which worked off DC. And then with the microprocessor, a little bit of code, we managed to get some pulses out which are proportional to the DC current. However, it was never going to be that easy, was it? So in this episode we'll look at digital to analog converters, LM386 amplifiers, and then realise that a fully digital approach was not going to work either.
I don't think you should be doing that.
So after a lot more thinking, I hit upon a new approach using the best of digital and analog world combined, and this seemed to work. So I progressed to a Vero board as some of the breadboard connections were getting a little bit intermittent. And then at this point there was no going back. It was onto the prototyping stage, laying out a PCB design, and then waiting for the boards to come back from the fab shop. And finally, we had something which worked. So as you can see, as soon as we switch the kettle on, it comes up on the Myenergi app. Look on the Fox app. It's as if nothing's happening because it samples every 5 minutes. And this is part of the problem. Anyway, sit back, watch me try and work this thing out. Welcome to episode 2. Okay, so because this is an electrical project, just a couple of things just to make clear. This is only using very low voltages, so I'm using 5 volts DC for the Hall effect sensors, 5 volts DC for the Arduino Nano, and I've got 12 volts AC to control the Harvi. I'm not going anywhere near the high voltage DC for the PV or the batteries. Second thing is, this is just, it's not meant to be a tutorial, it's not a guide, this is just a documentation of me building this project, and just for a bit of entertainment for you to follow along at home. Okay, so with that being said, kick back and let's enjoy the video. Okay, so after a lot of playing around with this, I've got something that kind of works and I'm reasonably happy with. I've also found where the limits of the Uno are. I've managed to sort of push it to as far as I can go. Let's just see if we can get this proof of concept to work. So I've got the Uno there generating the signals. We'll show you that in a minute about what's going on there. So it's generating a sine wave. But of course we haven't got our digital to analog converter as an output on these by default. I think you have to go have a reasonably high powered processor for that. So instead I've got this little unit down here, it's an MCP4725, and that's our digital to analog converter. So it's taking the digital pulses out that are coming out the I2C bus, and I'm using pins A4 and A5 for my data and my clock, and they're going into there and they're converting those pulses on the PWM signal into an analog sine wave again. Trouble is, there are limitations with that because there's a certain frequency that the PWM signal works over, and that gives you a certain pulse length in time, and then because you've got to allow that amount of time to develop that pulse for it to kind of start and stop, whatever that pulse width is going to be, that turns into a limitation in frequency. Now I've managed to boost that and get it as good as I can, so I'll show you what I found and kind of what we're going to run with. So if we look on here, you can see 2 signals there. So the top one is the PWM signal, and you can see it's bouncing around ever so slightly. I don't know if we can zoom in a little bit. Yes, it's just slightly jittering. We're right on the edge really there. And then the bottom one is actually what's coming out digital to analog converter. So that PWM is looking like that sine wave there. It's pretty good. You can see it's a little bit blocky, a little bit steppy. We can make it look a lot nicer than that, but then we really struggle. In fact, this dances around too much, so it's not really keeping up, which I'm not too happy about. I want to make sure I've got nice clean signals because there's going to be enough problems in this project as it is. Okay, a bit more progress. So we've got the Uno there and it's putting out the PWM signal out of the I2C bus there, and that's going into the digital to analog converter. So we're getting our nice analog sine wave out of there, 50 Hertz. I've got a little potentiometer here. That was just in case we needed to sort of move that signal up and down, but I've just got it at maximum, so it's absolutely fine. It could have gone straight into the amplifier, and this is an LM386 amplifier running it off. I think we're still running off the 5 volts off there, and then we've got our signal going in on the red one there. Then we've got a little variable, it's a 10k potentiometer and then that's coming out of here. This would normally be into speakers or something like that, so I've just simulated that with a small value resistor, and then we got that going through an ammeter. Now that's going to have its own resistor in there, so the value is not really accurate. All I wanted to prove out here is if, you know, what kind of levels do I need to get. I think we need to get is 1 milliamp AC into the Harvi is 1 kilowatt. So we probably want to be able to go to about 7 milliamps, which is 7 kilowatts, and then all the way down to 0. And then we're scoping those there. So the blue is the signal coming out of the digital to analog converter, so that's our sine wave coming out and going into the amplifier. At the moment I've got it turned down, so the yellow one that's coming out there is quite low and basically 0 on there. And let's see, it's very sensitive actually, so this might be a bit of a problem. But we'll just try and bring that in ever so slowly. So, oop, yeah, this has already jumped too far. There we go. So just put a little bit of amplification on, because this goes up to 200 times, this unit. Let's see, we're climbing up there. Let's see if we can get it to around 1. Alright, there somewhere. So we got our signal coming out yellow. We're at 1 milliamps, that'd be 1 kilowatt. Up a little bit more. 2 milliamps, that'd be 2 kilowatts. Starts to distort here. Whether that's a problem, I mean, it's still putting the current out, so maybe that's all that matters. Up to about 6, 7, yeah, then it just goes too far and the signal breaks down. So yeah, maybe there's our 7. Can we go all the way back down again? Yeah, down the other side. There we go, down to 0. Maybe that's a step forward. I think it is anyway. So the question is where to go next. Okay, quick update. So I was up pretty late last night till about midnight, and now it's early on Sunday morning. I'm still going here, but made a good breakthrough, which is why I kind of hung on last night. I got my coffee to get me going, and as you can see on the screen, there's quite a lot of exciting things going on. Okay, after quite a few more hours work, made some progress. Got a pretty nice system now, and I've got the code updated as well. And I've got the scope working there with a couple of signals. Explain what those are shortly. Okay, let's take you through what we got then. So I need to start around the back here. So we're sampling the mains using a regular CT clamp there, and I've just put it through several times just to amplify the signal. That's just give me a reference for the mains. That one in particular is going into the oscilloscope, but it could be anything really. They should all be pretty much in phase wherever I select it. And then each of those peaks there, you can see it's kind of trying to do a sine wave, but there's very little current going through here. It's about 0.1 amps or something like that. But anyway, it's enough just to lock on to where the peak is. And then over here, I've got power supply running through this power resistor, and then that's the, there we go, the Hall effect CT clamp. So I've got a ferrite core with the Hall effect probe in there with the 3 cables, and that's giving us our 1 to 4 volt signals out. That's going into the Uno, and then that's doing a little bit of processing, and it's going into this amplifier. We're just using the first one here, the other two are the same. That's amplifying it and boosting the current in particular, and then that's going out here, and we're looking at that signal on the screen. We'll see it in a minute, it's the blue one, but it's 0 at the moment. And then, yeah, we're looking at the number of milliamps out on there. Now the actual amount of milliamps doesn't matter, we just want to see that it goes up and down in proportion to the current that's in here, because there's a bit of calibration yet to go. So, right, let me give you a demo. Okay, so what I'm going to do now is just increase the voltage, and you'll see, we'll take you through the blue peaks that appear on here. So let's just increase that. Let's try and keep it so you can see all 3. That's the current in milliamps that's coming out of the amp. So that's ultimately what we're going to the Harvi. It'll tell it what the current is. So I'll just boost this ever so slowly. Just want to get maybe about half an amp or 1 amp. Otherwise that resistor gets quite warm. Somewhere there. And there we go. And let's go to half an amp. There we go. So that's going through that burden resistor, and then we're just measuring the current there, and that's going into there. And then we're amplifying that signal, and here it is. So you can see, yeah, it's a little bit low, so it's jumping slightly. So you can see the blue signal there, it's triggered every time the mains spike kind of goes up. So in the software it's looking for that rise, and then it triggers a pulse of a certain length, and that length varies depending on the current that goes through here, and that puts more milliamps out there. So, and because it's a fluctuating signal, it'll behave if you integrate the area under that, like an AC signal. When you integrate it, it will hopefully pick it up, and it will detect that it's an AC signal for the current. Right, so let's just go a little bit further, and what you'll see slowly is this starts to widen, and you might also be able to see the number of milliamps goes up on there. So try and get both in shot. Okay, I don't want to run it too long because the resistor gets quite hot. It's rated at 50 watts, but still gets very hot. There we go. So it's getting wider and wider on there. We're getting more milliamps. So maybe 9, 10. Yeah, at 55 watts. So we'll leave that now. But if I'll briefly whiz this up so this doesn't overheat, and you'll see the peak goes quite a long way. There we are. So hopefully using that, and a bit of calibration, and a bit of setup, should be able to measure the DC current going through the battery. Either way, I've got to work out how I'm going to do positive and negative yet, and we'll see what happens in the system. And we'll be able to also measure the PV panels as well. Right, that's progress. Well, a little bit more testing, it turned out that pulsing didn't work, so I needed a much better method. So, on to sine waves. Okay, so we've got our Arduino down there. Into A0 we've got our mains reference signal. Into A1, that's the signal that we get from the CT clamp here, measuring our DC. Now in my case, I've just got that across a voltage divider, so I've got 10k and then a variable 10k down here, and that's giving me a range of voltages that I can send into there and kind of simulate this measuring a DC here. It just makes life a bit easier and not overheating and cooking this resistor and so on and so on. Let's put some current through here, which is a bit more, another step closer to reality. So all we need to do, so we've got that powered by 5 volts and 0 volts on the Hall effect sensor, and then it's just got a signal coming out there, and we'll put that. So before we had the voltage divider into A1, and now we're going to plug that into A1. Right, I've put the sensitivity gain up in software by a factor of 4. It's still a bit warm, but and really we're getting a signal out. Yeah, I think there's some drift going on. Yeah, not the best thing to do things on, is it, on a breadboard and everything? Maybe we'll turn this on so it'll stabilise a bit. Okay, so down here we've got our little battery symbol. So that's currently, although that's 0, it's waving between 0 and 0.2. So obviously we've got to do something on the calibration to get that to be 0 when it is 0 there. But what we're looking for is, does the signal change? Now, just trying it off camera, it did rise up to about 2 kilowatts. And then even though the signal got bigger and bigger on here, this kind of plateaued and then went back down again. So there's obviously something not quite right in the signal. But, it's small steps. So let's boost this up. Let's go to 1 amp. And we should see the signal on there grow, the blue one, yeah. Obviously it's pulsing. Still 0.2. Let's see if it'll update. Oh, at 1.6. So let's write that down. Oh, yeah, actually that's what we got last time. 1 amp, 1.6. 1.4. Okay, let's go a bit more. Let's go to 2 amps. See, the signal's getting really big on there. It's pulsing a lot, and that is now reading. It says 1.2, 0.5. I think there's something it doesn't like still. Maybe I've got it. The fact that it's got that warble. I've got a low pass filter on the output. Oh, it's got to 2 kilowatts now. Maybe I just need to and it's coming out. Whereas before it was going in. And we've got a little bit of a phase delay. Have we? No, it's rolling. Phase is rolling. Okay, more to do. Okay, it's a few days later since the last time I actually recorded something. I've been playing around with it pretty much every day. I must have put 50 hours into this at least, if not more. I think the family's been very understanding so far. So, what have we learned? Let me just give you the highlights rather than just, demonstrate each failure, if you like. I'll just try and talk about some of the things and some of the wins as well. Right, where to start then? Oh yeah, so the pickup, the yellow one is the AC reference signal. So that is a CT clamp, I'm going to call it a voltage style CT clamp. So it's got a burden resistor in it that's wrapped around the live signal that goes into the oscilloscope. So it's getting a bit of a reference for the mains. Just try and get that to trigger properly. That's a bit better. So that's our mains pulses. Yeah, that's fine. We'll come back to why it's, in fact, it's offset in a minute. There's some issues with that. It's not perfect. So I've gone through a few things, which we'll get onto. I tried a different CT clamp. So I tried the one that's not got a burden resistor in it. So the type that you generally need to use with the Harvi. So it just generates current, and that just goes straight into the Harvi, and it sorts the signal out from there. The problem I had with that is then you're dealing with currents and very small currents. And as soon as you try and do anything like filtering it, high pass filter, anything like that, low pass to clean up the signal, there's just not enough current generation, and the signal basically just dies to almost nothing. So yep, we could look at op amps, of course, and maybe I'll end up there. But for now, the best sort of signal, I can get the cleanest signal, the nicest signal, is to do it all in volts, high impedance type stuff. So then you're in. It's a bit nicer dealing with that. You're not trying to amplify very small currents. So that's what we've got now. We've got voltage out there, so that's good. We can get pulses, that's good. You'll notice, so I've not got any offset here. So you'll notice that the AC is offset towards one side, and that's causing me a problem. We'll get into that in a minute. Right, what else have we learned? I've also learned that, I've got a digital to analog converter here, so that once I had generated PWM pulses out of here, with varying signals, 0 to 255, depending on the strength that I want to send out to the Harvi, in other words, the strength of current. If I run that through a digital analog converter, I can get a sort of sine wave, but it's really rough, and it wasn't ideal, and I was feeding that to the Harvi, and I was having all sorts of problems keeping it all in sync, because what I was basically doing was waiting for the signal to rise above a certain point, so it's definitely out of the noise, if you like, and then triggering the generation of a sine wave based on the lookup table, and the sine wave played one sine of 50 hertz, so 0.02 seconds period. The problem is, because you're waiting a little while before you trigger, you have to start partway through that sine table, so you're already into the sine wave to make sure it's in sync, and you have to finish a little earlier at the other end, so finish before you've done the full single waveform, so that you're definitely in time to be in time for the next trigger. Because this is not exactly 50 hertz, it's plus or minus, I don't know, half a hertz, something like that. And if it finishes early, then you'll miss one, and basically you'll have to wait till the next pulse, and the whole thing was sort of occasionally jittering and jumping around. Whole load of problems. I've decided I'm not going down the route of artificially generating a sine wave and triggering it off the mains. It's just too unreliable, doesn't work. So, new plan. Okay, I think it's time for a new plan. So I had a look at some of my wiring diagrams, some of the previous notes I'd made, drew up some new schemes, thought about if they were going to work or not, tried to put some kind of new plan together. I had a look back over some of the sensitivities of some of the equipment I was using. This is the Hall effect, to see if I could do something different. Had a look at a whole range of different op amps, summing, integrating, whole range of different types. Every kind of op amp I think you could think of, I had to think about, and then went back to some of the footage I'd done earlier, and then also went back to completely analog, so there's no digital processing in here at all, just trying to do everything in the analog world, but it was really difficult to control. It's surprising what you can do with the digital world these days. So again, it's back to the drawing board and time for something new. So what we needed is the best of both worlds. So I looked at op amps, so all kind of things really. So this kind of thing. So there was I had the unity ones, the buffering ones, if you want to buffer between an input and an output, so match your impedances that way. I had various gains on them, positive gain, inverting, non-inverting. Now one thing to note with op amps is in most cases, especially with signals like this, you need a positive and a negative, and then a zero reference in the middle. And yeah, you can at a pinch do that with two resistors, but it's very unstable and it tends to wander one way or the other. So I'll put it on the screen here. Can't quite remember the number, but Texas Instruments do a virtual or a ground, a true ground that really holds that rock solid in the middle. So if you've got 12 volts across here, it will give you a perfect 6 in the middle, and then you can drive your op amps that way. Anyway, we don't need to worry about op amps because I'm not using them. Some other issues were actually getting enough current to come out, because you're only coming out of an Uno like that, which only a few milliamps. Yeah, you can run it through transistors, try and boost it up that way. I had the classic 386 amplifier here, it's like an audio amp. I couldn't really get that to work. And I also had this, which was a voltage to current. So I think up to 5 volts comes in and you get up to 20 milliamps out. I couldn't get anything to work out of that. Maybe it doesn't like signals that go above and below positive, like actual audio signals. I don't know. I couldn't get that to work, all that to work. And I was kind of on the verge of giving up with it because I must have tried 20, 25 different iterations of combinations. I got a new idea. Oh no, it doesn't work. I got a new idea. It doesn't work. And finally, I have got, so far, I haven't had any issues. I've got something to work, so let me take you through some of the details. It kind of started over here. So this dangerous looking device that I've made, this started life as normal wall transformer like that, and we got a 7.5 volts out DC. I don't want DC because what I thought was, hang on a minute, if I plug this into the mains, obviously that's mains voltage. Inside here there's a transformer, there's the rectification, so you've got your full bridge rectifier, and you've got your smoothing capacitor, and there's a little filter capacitor as well in there. But if I tap off when it comes out of the transformer, I'll get AC. I can't remember, I think I've got 14 volts AC, can't quite remember. And that's what this dangerous little device is about. This gives me AC completely in synchrony with the voltage. So I'm getting a signal out here, but it's 14 volts AC. I obviously needed to step that down to, I think it was 5 volts AC to go in the Harvi. So I used a pair of resistors to drop that down. Now there's some downsides to doing that, we'll get into that in a minute, but I'll just try and prove the concept. So my AC signal comes in off the mains through there, I drop it down, try and limit the voltage, and then I just vary the resistance using a light dependent resistor in that circuit, and then it goes out to the Harvi. I don't ground it, it's all floating, it's all self-contained. And that works. So you might be asking yourself, how do I vary the resistance on that light dependent resistor, and how am I linking that to the DC? Let me show you. So in terms of what I've got mocked up here, which looks lethal I know, but I've got a power supply here, and then I've got a coil of wire going through that just to amplify the current, because I'm only running low current here. That goes through this clamp that's got the Hall effect sensor in it and a ferrite coil, and then that is what's going into the analog input of the Nano, and then I've got 5 volts and 0. There's the 3 cables that you need to run the Hall effect. So as I vary the current through there, that comes through this high value resistor, if you like, that you can get put lots of current through, I get a reading on that. Good. Okay, so what does that do? Well, that goes in the Arduino and it reads that voltage. So normally if there's nothing, it's 2.5 volts. If you've got full current going one way, it's up to 4 volts, and full current going the other way, it's down to 1. So that gives you a range as to what's going on, and it's proportional to the current flowing through this wire. All good so far. So you read that voltage in, and then you simply map that. There's just not much code to do it actually. Map that onto a PWM signal that comes out of pin 9 in this case. And the PWM signal goes into this end here through a resistor, or in fact 2 resistors to get the current manageable, into the LED, and it varies the brightness of the LED. That then goes on to an LDR. So inside that tube, they're just facing each other. LED this side, light dependent resistor this side, and this is on this separate circuit, which basically limits the current coming from the mains AC. So it comes through here, limits the current on that. There's another limiting resistor just to keep it in the range. That'll eventually be a trim pot so I can calibrate it. And then that goes into here. Now this is to allow you to switch it over, positive and negative like that, well, however you want to think about an AC signal, but anyway, one sense and the other sense you can flip the direction. And that's because if the current goes below, if the current is reversed, then the voltage out of there goes below 2.5, and if it's the positive direction it goes above 2.5 volts. The software checks that, so if you're going one way it just joins the wires that way, and if the current's going the other way, it switches the relay which swaps those round, and the current goes in completely 180 degrees. So you've either got it aligned to the voltage, so the power's going one way, or you're 180 degrees out and the power's going the other way, so it knows which direction it's going. And all that works. So let me hook. Yes, there's one thing I need to know. I'll bring you in close. Now, purely for demo purposes and purely to get this thing working, I've got a pair of resistors there to drop that AC voltage down to something manageable that can go into the Harvi. These are only 1/4 watt resistors, and I ran the numbers and I thought it was going to be a bit borderline. They're going to get a bit hot, and yeah, they do get a bit hot, very hot to the touch. So I've got some 1 watt ones on order. Now, we all know this is not the best way to do it, and as you draw current out of that system, let's say that's 12 volts across there in the middle, 7 volts. As soon as you draw some load off it, which you will, that center tap point wanders quite a lot. Now, I might get away with it because the Harvi doesn't care too much about the voltage that's going in, only the current. As far as I can work out, the current is proportional to the LDR in here, so it might just work, so we might get away with that. The problem I might have is if I want to tap another circuit off that, because this will run the battery, so I can say plus or minus on the battery. If I also want to center tap off that center voltage and run one for the PV panels, if this is drawing current, it might upset the other one. In other words, if I'm showing the kilowatts on the battery and showing the kilowatts on the panels, and the battery one moves, it might interfere with the panels reading because it might skew this. If that happens, I've either got to have another voltage divider and pull the current off separately, or worst case, have another AC input that's dedicated, one line for each sensor. Yeah, I don't know, we'll try it, but that's kind of what we got, and it's as simple as that at the moment. So apart from putting a variable resistor in there, uprating those to 1 watt, hopefully that will at least get me by. That's kind of it. Well, I guess before we go and set it up back on the inverter, we can show you it working here. So I won't plug the AC in yet because the resistors get pretty hot pretty quickly. So we'll just show you one side of the system first. So what I'm going to do, I'm just going to put some current through here, which will load up this resistor, and then that will put current through our Hall effect. And then you should see that on there. In fact, we'll zoom in a bit on the time base. Yeah, on there, so we can see the pulses. Right, we'll do that first. Just put a little bit of current on. Going a bit more. So on the yellow trace there, that's the PWM signal that's going into the LED. I think it's in frame. Yeah, so you can just about see it starting to glow there. So if you watch that, if we go a bit further, yeah, it glows more and more and more and more. So turn the current up, brighter and brighter and brighter, and you can see that the pulses get closer and closer together as we put more and more current through, and eventually you'll get 255, which is the maximum. Now if you go too far, this will roll round, but in reality that is calibrated, so it won't do that. Yeah, so you go too far. So that's your maximum, and then you go all the way down to the minimum. So that varies the brightness, and that varies the resistance on the LDR. So that's half the circuit. Okay, so let's show you the other side of the circuit now. We'll plug our, this is AC coming into here, like 14 volts AC or something. Oh yeah, I should mention, rather than that dangerous device over there, I've got an AC adapter, so you can get these for powering laptops. Obviously your DC one would not work, so we've just got a transformer in here and that's it. So we've got AC coming out like 14 volts or something like that, and then that's what we're modifying. So you'll see the result appear on there when I change the current. So the current will change through the DC part, it will change the PWM, change the brightness, changes the LDR resistance, and that reduces or increases the resistance on the AC side that's coming out of here, and then that's what's going up to the Harvi. So anyway, here we go. I think it's just out of shot, but I'm turning the current up on the DC side, and then it's coming out as AC over there. 8 milliamps, 9, 10, all the way back down again. And you can see varying the brightness of that, and that's changing the resistance and the milliamps there. And to be honest, that's kind of it. Oh yeah, the only thing to show you then is if I switch the direction around over there, as if the power's coming into the battery or out of it, you should see these relays click and it will flow the other way. Now on that, I think it just shows positive, whatever. I don't think the AC goes negative because that probably doesn't make sense. Just giving you the RMS, isn't it? But hopefully it will show the reverse direction when it's used for real. So we'll just swap those over. So this is if simulating, so you were charging the battery and now you're discharging the battery, or the current is going a different way. So you'll see these click on when I turn this. So they've clicked on, and you'll see the positive again because it's just taking the RMS, but effectively it's done a changeover like that. So what was positive is now negative, however you want to think about AC. Now in the final implementation, maybe I can do this with a couple of MOSFETs or something like that, but you know, for now this works. Yes, after, I don't know, 4 or 5 weeks, probably 50 hours invested in this, loads of blind alleys, loads of dead ends, I've finally got this thing to work. So I've got the proof of concept right here. What is it? Well, these are my DC cables going into a hybrid inverter, and normally you wouldn't be able to detect those with a regular CT clamp like we got down there, but I've got this homemade custom clamp, goes into this box of tricks, and then over here on the app I'm actually reading the kilowatts coming out of that DC line there. If you look on the front here, now the battery is fully charged, so everything you see there is coming off the panel, so let's say it's 2.5 kilowatts. And if we look down here, so that one is what's coming out of the inverter, 2.5, that's that CT clamp down there around the live cable, so we trust that, you know, that's AC, proper CT clamp. And then this one here is this circuit here, what it's putting out through there and kind of faking it into the Harvi. And you can see it's sort of close, and I've just been playing around. I've been playing around with this potentiometer, trying to get them to match. Why am I doing that? Because obviously it looks like I've got both. Well, the house is getting very confused because it thinks now I've got 2 sources of energy coming in, 2.5 kilowatts each, and clearly we haven't, we've just got one. I'm just reading it in 2 different ways. So what we'll end up having to do is, once that's working and the same one for the battery, we'll switch this off, and then it will add this one and the new battery one together, and it will be back together again. So at the moment the complete reading into the house is wrong, but all we care about is do these match, especially as we go through the kilowatt range, if you like. Now I can't control the sun, so we're just gonna have to wait till this evening and just see how when the sun goes down and this goes lower, does it track, and see what we got. Okay, so here was the next logical step from the breadboard up to this kind of multi-purpose Vero board. And you can hopefully see the layout here. We've still got our incoming here, it's filtering. We'll go into this in a bit more detail, the Arduino, and then all the output processing. I had a little mini breadboard here and a couple of little options that I tried just to see how it was all going to work and what was going to be the best layout. So at this end here we've got our jacks. These are for the DC CT clamps, the Hall effect. So we've got one for the panels, one for the battery, and they've got 5 volts, 0, and then the signal in here. I went for a fairly big capacitor in the end and resistor network. I think it was filtering below about 0.1 hertz or something like that. You really want a nice clean input. You don't want any waviness on it or anything like that, otherwise it will just keep tripping whether you're passing 0. So nicely filtered. And then these 2 buttons here, one is for the 0, or these are both run the 0 for one's for the photovoltaic panel, one's for the batteries. So when you've got no current flowing at all, you can just press that, and then the software knows where 0 is and it can move from there. And then potentiometers. Now I had these configured in a variety of different ways. One of them was to initially to set the 0 point, but it wasn't very handy, so I used the buttons for that in the end. And then the other option was to use them as kind of a calibration, fine-tuning, and that's ultimately what I went for. So, you know, you can probably see there's lots of modifications, but that's the idea. You're trying to play with it and see what works best. And so they're all the inputs, and then the outputs here. They go over to these are the LED and light dependent resistor sort of coupling systems here, heat shrink to keep the light out, one for the panels, one for the battery. And then I've got little indicator LEDs here, so whatever current and voltage is going to these, whatever PWM signal is going to these, the brightness, that's reflected here, so you can sort of see what's going on, because obviously they're hidden behind there. And then we got our resistor network. These are 1 watt resistors, I think 220 ohms, something like that, because I needed to make sure there was enough current coming out, otherwise there wasn't enough current to run the Harvi. Downside is you need, with the low resistance, to get that, keep that current, you know, they get quite warm, not hot, but they are warm. And that's a voltage divider that brings you from the 12 volts AC down to, I think it was 5 volts AC that the Harvi needs. I couldn't find a 5 volts AC supply from mains. Maybe they make them, but I couldn't find one. I could only find the 12 volt one. So I think it's to power a laptop or something like that. So, you know, at least it's readily available if I need to make a couple of these, or, you know, need to make some better versions in the future, whatever. So that's that. And then I did have some switchover system here, sort of an additional relay board that allows the the current to swap round like that to see if if the battery current is going positive or negative. You need to just swap that over. So I had a system there, and here I was just playing around with the best way to control the current. And then over here I've got the 12 volt AC input. I've got two of those. Now originally I had it all running off one 12 volt AC transformer. I don't know if I completely, this is the right conclusion, but what I was finding was that as soon as you started to vary the current in one of the legs that went off to, say, the panels, the panels were getting a lot of sunshine, a lot of current, it seemed to be affecting the current in the other half of the leg because they both came off the same transformer. Now, I don't know if that was because this is the early stages of development, and actually if I went back to a single supply, maybe it'd work. Now I've ironed all the bugs out. But anyway, I've stuck with two independent transformers, so they're completely separate. The PV and the battery current circuits are completely independent. They only join up, if you like, when you're on the mains side. Obviously, they both feed from the mains. And so hopefully that's enough of isolation so they don't interfere with each other. And then the rest of it, so we've got our outputs off to the Harvi for the photovoltaic system and for the battery. So that's how it was laid out. Now, I'm not an electronics expert. I had to work really hard to get to this point, to get it to work, and teach myself how to use that easy EDA software to draw it up and then get all the connections and make sure I'd order all the right parts. It was going to go together. So I'm really pleased with myself that I managed to get this far, that's for sure. If you are an electronics expert, you probably see a few things you're not very happy with. Really using an LED to control an LDR to vary the resistance is probably not the best idea. I tried loads of different things. As soon as you start interfering with this current that goes into the Harvi, trying to do something, artificially create it, whatever, I just couldn't get anything to work. It just, it's got to emulate a CT clamp, a proper AC one. And this one, putting a little bit of resistance in the way seemed to be the best way to do it, or that I could find anyway. Now I know, well, there's a couple of things to say. There's a response curve of these that isn't linear. It's kind of exponential or power shaped, so all of that has to be taken into account. I had to do a curve fit in Excel and work out the parameters and put that into the software to try and linearize it effectively. So I had to do all that kind of stuff. Also, these will be affected a little bit seasonally over the year when they get warmer and colder, although in our workshop here it tends to be reasonably stable, not too bad. It's not like it's in the loft or anything like that. So they will vary a bit, so it will probably go out ever so slightly over the year. I don't know in terms of its calibration. But it's for indication, and it will give me a pretty good idea about what's going on. Obviously these are just stuck into these little header blocks at the moment, and I did have it so that it did stop working at one point. I had to bend the legs. Really, they need to be soldered on properly, but I did it like that because I thought I might have a little daughter board on here, because I didn't know if I'd need one, two of these. These are different sensitivities that I tried. I've tried different LED colours. This is currently white. I tried red just to see if I could get the kind of sweet spot for where the LDR was most sensitive, or how it was going to give you the most linear response and the kind of sensitivity level I wanted. So I was able to plug and play a few different ideas here and settled on this one, this arrangement for now. So, and I guess you could say using a relay just to swap the pairs of current, sort of the polarity over to change the direction of current, or the kilowatt shown on the app. Maybe that's a bit lazy or a bit not the right way to do it. I don't know, maybe there's some H-bridge type arrangements you have on stepper motors. Maybe that could have worked, but any interfering with the AC current through here, anything that puts too much resistance in, I've already had to have very, very low resistances to drop that voltage down. Anything that messes around with it too much and the whole thing just stops working. So yeah, I know, but it does seem to work, and for now that's working really well. So that's kind of it. That's kind of what we got, and really pleased with it. Next time we'll machine up an enclosure, which is a bit more what this channel's known for. So we'll machine it up out of some aluminium, and we'll use the lathe just to turn the side posts there, and then use a little standoffs just to put the circuit board in. and I decided to use a nice smoked plastic there for the lid, and then machine some outlets for all the cables. And once I'd finished that, yeah, I wasn't that happy with it, so I made a better one. So this one's got a screen in it, an LCD screen, and it's got some buttons so you can operate a little menu and change some parameters. And here's a little sneak preview of it installed. I think it looks rather smart. Alright, I'll see you next time.